Hello and welcome to this lecture on advanced electric drives. In the last lecture, we are discussing about the tractive effort and the drive rating. When a vehicle is moving, when a train is moving, it requires some tractive effort to continue its motion. And the tractive effort is because of various components in the locomotive or in the train. Imagine a train is moving. When a train is moving, it has to accelerate horizontally. That is basically the horizontal acceleration. It's having a huge mass, so it has to accelerate horizontally. And then there are so many rotating parts like wheels, axles, the motors. They also have to accelerate rotationally. So we need some tractive effort or the equivalent torque to accelerate the rotating mass. And then sometimes the train also negotiates or overcomes a gradient. When we say that the train is having a gradient, it can be up gradient or it can be down gradient. The tracks may not be level, it can going up the track or maybe going down. That is because of the gradient. So it has to overcome that gradient. And then again the train has to also move against the friction. The friction could be the air friction, could be the friction with the wheel and the rail and the internal friction. So we were trying to evaluate the component of tractive effort for each of this. Let us recapitulate what we have discussed in the last lecture. To accelerate the train horizontally, we just find out the train motion in this following fashion. So this is what we have here. Let us see the various component of tractive effort. Now tractive effort to accelerate the train horizontally. So we have the train mass in ton m. We can find out that in kg by multiplying in 1000. Then alpha is the acceleration which is expressed in kilometer per hour per second. So we can convert that into meter per second square. Kilometer into 1000 will be meter, and hour, 1 hour is 3600 seconds. So we can convert the acceleration into meter per second square, and then what we finally have is the tractive effort in Newton. And then to accelerate the rotating parts of the train, so we have the wheel, the moment of inertia of the wheel, and we have nx number of axles. So we have 2nx number of wheels. So this is the total moment of inertia of the wheels. And then we have the gear ratio A, which is N1 by N2. N1 is the teeth on the motor side gear and N2 is the teeth on the axle side gear. So we can take the ratio of N1 and N2, and that is the gear ratio, and we can convert, this is Jm is the moment of inertia of each motor, and we have n driving motors, by A square is the moment of inertia J2, that is the moment of inertia of the motors referred to the wheel side. So if we add these J1 and J2, we get the total moment of inertia of the rotating mass, and this rotating mass has to accelerate rotationally. So we have to multiply this rotating mass with the angular acceleration, and we can calculate the angular acceleration from linear acceleration by dividing the linear acceleration by r. R is the radius of the wheel in meter. And then we can find out the equivalent torque. The torque is the moment of inertia into angular acceleration, and then we can divide this torque by the radius of the wheel, and then that gives us the tractive effort for angular acceleration of the rotating parts. And if we want to find out the total tractive effort because of acceleration, by acceleration we mean both linear and angular acceleration. So we have two components. One component is for the linear acceleration or horizontal acceleration, that is Fa1. The other component is for the angular acceleration of the rotating mass, that is Fa2. If we want to find out the total tractive effort Fa, that is equal to Fa1 plus Fa2, and that will be giving us an equivalent mass of the train, and this equivalent mass is calculated as follows. So, we have the total tractive effort Fa is the sum of the linear tractive effort and the tractive effort for accelerating the rotating parts Fa2, and we add these two components, and then what we obtain is the equivalent mass me of the train. That is not just the mass in ton, but it is something higher than that, that can be calculated in the following formula. We have to know the moment of inertia of the wheels, the number of wheels, the moment of inertia of the rotating or the driving motors, the number of driving motors n, the gear ratio a square here, and then the radius of the wheel. So, this expression will give us the effective mass me of the locomotive. Then the second part of the tractive effort is to overcome the gradient. The gradient could be up gradient or it could be down gradient. Suppose the train is moving up the gradient. So, we have a component of force which is opposing the motion. We can calculate that force in the following way. We have the train moving upwards. This is the weight of the train, that is 1000 mg. This angle is theta, and we have a component of this force which is opposing the motion. So, we can calculate this component, and this component is 1000 m into g into sin theta. So, sin theta here is approximately equal to g by 1000. G is the gradient, and it is usually expressed the elevation in 1000 meter. So, we can find out sin theta dividing g by 1000. So, we can substitute sin theta by g by 1000. So, what we obtain is the tractive effort in Newton, m small g into capital G, and then finally, if you want to find out in kg, we can divide by small g, that the acceleration due to gravity 9.81 meter per second square. So, we get the tractive effort in kg. And then we go forward to find out the fourth type of tractive effort, that is the tractive effort required to overcome the train resistance. Now, this tractive effort is difficult to estimate, because this resistance means it could be internal resistance, it could be external resistance, it could be resistance with the air or the friction with the air. So, this is basically modeled as Fr is equal to A plus Bv plus Cv square in the following way. So, if we want to find out an expression for this, it will be a complicated expression as follows. So, this Fr is equal to A plus Bv, V is the velocity of the train, plus Cv square and so on, and it is in Newton. So, difficult to estimate. So, this is difficult to estimate. So, instead what we do, we find out this resistance as a function of train mass. If the train mass is capital M in ton, we say that the train resistance is R into M, R is small r, and R is defined as the Newton per ton. So, this requires this much of tractive effort to overcome the resistance. It means if the mass is more, the resistance will be naturally more, because if you have higher mass, there will be higher internal friction. So, it is quite justified that we can have approximate expression for the train resistance if R is equal to R into M. So, we can say here if R is equal to R into M, where R is approximately 20 Newton per ton. So, we can evaluate this, and this will be in Newton. So, this is the tractive effort for overcoming the train resistance. So, if we want to find out the total tractive effort, F T is equal to F A is the tractive effort to accelerate the train horizontally and also the rotating parts of the train, plus the tractive effort to overcome the gradient F G, and the tractive effort to overcome the train resistance F R. And if we simplify this, or if we write the expression for each one of this, we have in kg, if we write down the expression in kg, so we have 28.3 ME into alpha. The gradient could be plus minus m into capital G plus mr by 9.81, and this will be in kg. And if you want to find out in Newton, we can multiply this expression by g, small g. Small g is the acceleration due to gravity. So, we can also say that that is equal to 28.3 ME alpha plus minus mg plus m small r 9.81 into g in Newton. Now, after we have found out this tractive effort, we need to calculate the rating of the motor. Ultimately, the motor will have to drive the train to move it forward. So, when we want to find out the rating of the motor, we have to find out the equivalent torque that is reflected at the motor side. So, let us say we have n motors and we have a transmission efficiency that is eta. The efficiency is not 100%. We have a gear in this case like this. We are discussing about the drive rating. So, we have the motor here, and the motor is connected to a gear, and the gear is basically driving the axle, and we have finally the wheels. So, this is the motor, and we have the gear, we have N1 here and N2 here, and the gear ratio in this case is N1 by N2, and these are the wheels. And this is axle. And here we have found out what is Ft. Ft is the tractive effort. We have the train moving on the rail here. This is the rail. And the tractive effort that has to be applied here is Ft. So, if Ft is the tractive effort and we have the radius of the wheel is r, what is the torque that is experienced in the axle? So, we can find out that the torque at the wheel or the axle is equal to r into Ft, and the total torque at the motor shaft, here is the motor. So, we experience the reflection in this torque at the motor. So, T t is the total torque referred to the motor shaft. This is the motor shaft. So, when we try to transfer the torque to the motor shaft, we have to take into account the transmission efficiency. This is the efficiency of transmission is eta, and then we have the gear ratio. So, we have A into R into F t divided by eta. So, we can call this to be eta t to signify the transmission efficiency. This is in Newton meter. So, eta t here is the transmission efficiency. The transmission efficiency is a mechanical quantity. It says how much of torque is transmitted to the motor, and transmission efficiency is a quantity which is less than 1. It could be something like 0.9, 0.95, and then it is reflected in the motor side. The motor experiences a higher torque than the actual torque that at the wheel side. So, this is what we have here, and then if we have n driving motor, so a T m is the torque per motor is equal to T t by n, and that is equal to A R F t by N t into capital. So, this is how we find out the torque which is seen by the motor. So, we can also find out the speed, equivalent speed at the motor side, because we know the gear ratio. So, we can also calculate the speed, we know the torque. So, we can evaluate the power, and once we know the torque and the speed, we can pick up a right kind of motor for the traction application. So, this calculation gives us an idea how can we choose the rating of the motor, and once the motor rating is chosen, we can go ahead with the design. Now, when we see the actual locomotive, the locomotive is drawing the power from the overhead line, and the power is usually brought in AC. The transmitted power is AC. So, what we do, we step it down and then we rectify it, then feed it to the motors. The motors could be DC motors or AC motors. So, let us take a look at the AC locomotive, in which we bring the power from overhead 25 kV line and then feed the DC motors. So, 25 kV 50 hertz AC traction. So, what we have here is the following. So, we will first choose on load tap changer. So, we obtain this power from the overhead line, that is 25 kV, and this is the transformer primary, and we have the transformer in the secondary side, which is actually a step down transformer, but this secondary side has got so many tappings. And we have a simple diode bridge rectifier here, a high power diode rectifier. And then we have a filter, and then we have the traction motors, the DC series motors. So, let us say we have the 4 motors here. So, we connect these motors in the following fashion. This is the filter inductor, that is LD. And then we have on-load tap changer. This tap changer is connected to the secondary side, and we have the diode bridge here, and this is the traction motors. And here we have used the DC series motor. And this is the transformer with tap. Now, when we have the transformer with tap here, the objective is to control the speed. The secondary side we have so many taps, and what we have in a typical tap changing transformer, we have 20 to 40 taps presented in the secondary side. And when we want to change the speed, we change the speed by changing the taps. In fact, what we do to start the machine or to start the motors, we apply a lower voltage. So, we start with a 0 voltage, and then we go on changing the taps, and thus we achieve higher and higher speed. So, this is a primitive type of control which is also still in use, and in this case we drive a DC motor, the tap changing transformer supplies to a rectifier bridge, the output is rectified as we have seen here. This is the rectifier bridge, and then we have a filter here which filters the ripple in the DC side, and then we have the 4 traction motors. We have 2 in series and 2 in parallel here, and this combination is used to reduce the current burden. We can use all in parallel, but if you use all in parallel, the current requirement will be higher in the AC side. We have the source current in this case. We choose to have 2 in series and then 2 combinations in parallel. So, what is the advantage? Advantage in this case is that it is an electric drive, but this topology has got lot of disadvantage also. Now, when we have a tap changing transformer, the tap changing transformer requires lot of maintenance. We have the mechanical tap changer, and they have to be immersed in oil, and they undergo wear and tear. So, they require frequent maintenance. So, one disadvantage of this arrangement is that the tap changing transformer requires periodic maintenance. Tap changing transformer requires periodic maintenance. In fact, when we change the taps, there is a jerky way of control. The control is not very smooth. We are in a lower tap, we are changing to a hair tap, there is always a current spike. So, there is a possibility of wheel slip. The adhesion is less when we are changing the tap. So, the second difficulty here is that we have discrete control. The control is not smooth, it is not a continuous control. So, we have discrete control, and hence there is problem of wheel slipping. Discrete control, possibility of wheel slippage during tap changing operation. So, instead what we do here, that we go for a different kind of topology in case we want to improve upon this situation. We go for a smooth control, and smooth control means we have to go for semiconductor based control. We do not use a mechanical control, because mechanical control is always cumbersome, it is having its own problem. It requires frequent maintenance. So, instead of having this mechanical control, what we do, we go for semiconductor based control. So, we have the same transformer, a step down transformer, because 25 kV is a higher voltage. Definitely we can't have motors for such a high voltage, we have to step it down. We bring the high voltage at 25 kV, we step it down, and then after stepping down, we do not use any tap changer there, we use a half controlled bridge, a half controlled single phase bridge using SCR, silicon control rectifier, and thus we get a smooth variation of the output voltage. And when we obtain a smooth variation of the output voltage, the speed changes smoothly and there is no problem of wheel slippage. The adhesion is better in case of a semi controlled semiconductor thyristor bridge. So, we will now discuss about the thyristorized control of traction motors. So, we have a 25 kV AC traction using semi converter controlled DC motors. So, let us see the power circuit here. What we have here is the input AC and the input AC is obtained at higher voltage, that is 25 kV, 50 hertz, single phase, and then what we have semi control converter. By semi control converter we mean two of the devices are SCR and two are diodes. So, this is a semi control converter bridge, and then we have an inductor here, and here we have the DC motors, and we can use separately excited DC motor here. Let us say we have two motors connected, and we have the secondary feeding the semi control converter bridge. Like this. What about the field winding? This have the field winding as well. So, we have two field windings, and the field windings of this motor are fed again through another semi control rectifier. So, we have semi-control rectifier here, and this feed the field winding. These are the armature. And the field winding converter is also fed from a secondary. So, this is the topology in which we have connected two separately excited DC motor fed from a semi controlled converter bridge. Now, what is the advantage here? The advantage in this case is that this semi controlled converter bridge can smoothly vary the output from 0 voltage to a maximum voltage. There is no changing in step, there is no discrete control, and hence we can have a seamless variation of the speed. So, let us list down the advantages of this kind of control. So, advantages are, we have smooth control of output voltage, hence the torque and speed control are smooth. So, we have, this is output voltage, we can say that this is the voltage that is coming out of the half control converter. So, we can call this to be VA, the armature applied voltage. So, this VA control is smooth, and hence we have smooth control of speed and torque. And then of course, it is a highly efficient system. We do not have any resistors, we do not have any losses here, because we have solid state devices like SCRs, and the SCRs and the diodes have got minimal losses. The efficiency is higher here. Higher efficiency. Since we have smooth control, we have no problem of wheel slipping. The adhesion is better here because we are employing a smooth control, and hence we do not have any sudden change in the torque. Adhesion is better. Better adhesion. Now, we can also list down some disadvantages here. Although this is quite attractive, there are some drawbacks of this kind of topology. The drawbacks are as follows. When we are employing the semi control converter, we have to be careful about the input current in this case. This is IS1 and this is IS2, and this current which is drawn from the supply we can call is the input current, that is IS. Now, when we employ a semi control converter, this IS input current contains harmonics. The input current is not sinusoidal. So, when the input current is not sinusoidal, they are basically rectangular current. The current nature is not sinusoidal, and hence they contain harmonics. So, the harmonics are drawn from the supply. So, number one, the input current are not sinusoidal. Hence, harmonic currents are drawn from the supply. So, in fact, when we draw harmonic current from the supply system gets polluted, and the power system also get polluted. So, we have the problem of power quality. And in fact, when we draw harmonic currents with the transformer gets overheated due to the increased losses because of the harmonic currents. And what about the other drawback? The other drawback is this, that in addition to harmonic current, this converter also draw reactive current from the supply. So, we also have a reactive current requirement, which results in poor power factor. So, in this case, the second disadvantage is the input current power factor is poor, especially at lower speed. That is at high value of alpha. Alpha is the triggering delay. So, when the speed is low, alpha is very high, because when the speed is low, the voltage has to be also low, and the voltage can be low when we have higher value of alpha. When alpha is high, the power factor becomes poor. So, these are the drawbacks of this kind of converter. Although this converter is very popular, this converter is employed in many practical locomotives, but one has to be really concerned about the drawbacks of these converters. The number one drawback is the harmonics, and then the current drawn is at poor power factor. Let us now see how the power factor of a single stage converter is poor and why the current contains harmonics. Let us try to understand that by drawing this circuit diagram. So, we have a semi control converter here. These are the two SCRs, and then we have the load here, we have the DC motor load, the traction motors, and this is obtained from the overhead transmission line to a transformer. So, we call this to be a single phase, single stage semi converter. So, we have only one stage here, and similarly we can also fill the field circuit. So, this is a step down transformer. Now, if we see the input current, this input current, let us say here is IS1. Now, if we have this input current IS1 and this current is IDC, and this converter is operating at a triggering angle alpha. Let us assume that this converter is operating at a triggering angle alpha. Alpha is the triggering delay. So, we can draw the output voltage with respect to the input voltage. So, this is our, these are our waveforms. So, the output here is VA, let us say, or VO, the output voltage here, and this output voltage for certain triggering angle will be like this. This is omega t in the y axis, sorry, in the x axis, and this is VO, the output voltage, in the y axis. Let us say the triggering angle here is alpha, and the triggering is symmetrical. So, we can say this is pi plus alpha, this is pi, and this is 2 pi. So, the output here will be of this nature. So, this is V naught. So, the V naught or the output voltage will be DC node out, the rectification of the input, and since we are controlling the output voltage, we have the triggering angle alpha, and up to alpha the voltage remains 0, and then from alpha to pi voltage becomes Vs, and then from pi to pi plus alpha, this is pi to pi plus alpha. So, the voltage basically remains 0 from 0 to pi and then pi to pi plus alpha. These are called the freewheeling interval, and then we have the output VO will be present from alpha to pi and pi plus alpha to 2 pi. Then we can also draw the corresponding current waveforms. So, we are more interested in the input current Is or Is1 here. From 0 to alpha, Is will be 0 because that is freewheeling, we do not have any current in the input side, and then from alpha to pi we have a block current like this, and then again from pi to pi plus alpha we have 0 current, and from pi plus alpha to 2 pi we have the negative half cycle. So, what we have here is this, we have the negative current, and the amplitude of this current is the DC link current. In the DC side we have IDC. So, this current is basically IDC, and similarly this is minus IDC. So, if we see that the input current is not sinusoidal, input current in fact contains harmonics. This is basically rectangular nature of current or called quasi rectangular current, and this contains harmonics. Now, if we find out the input power, we have to find out the output voltage here. V naught is the average output voltage, that is equal to, if the input, this is the source voltage Vs, that is here source voltage, and we can say that is equal to root 2 V sin omega t. In fact, this is the minus of that. So, this is the source voltage we have, Vs equal to root 2 V sin omega t. The source voltage goes like this in the negative direction also, and the rectification of that we have in the positive here. So, the average output voltage will be the average of this. So, we can integrate this from alpha to pi root 2 V sin omega t and d omega t, and this is over 1/2 cycle. So, 1 by pi, and if you simplify this, what we obtain is the following, root 2 V 1 plus cos alpha by pi. So, this is the output voltage, the average output voltage. Now, if we see the output current, the input current here is quasi rectangular nature, it contains harmonics. So, we can find out what is the fundamental component of the input current. So, in fact, if we want to find out what is Is1 is the fundamental component of the input current, IS1, and we take the RMS value here, fundamental component within RMS. So, it is 4 IDC by pi into cos alpha by 2, and for the RMS we divide by root 2. So, this is the RMS value of the fundamental component of the current. Now, we see that this current is delayed from the voltage by by alpha by 2. In fact, the current is lagging behind the voltage, because there is a delay. We are applying a triggering delay, the angle is alpha, and the current is lagging the source voltage. Now, if we draw this fundamental current here, it will look like this. So, this will be the nature of the fundamental current. We take this, and this has to be symmetrical here. So, this is the fundamental component of this. If you draw this, now this angle is alpha, and this angle is alpha by 2. So, in fact, it means the current here is lagging behind the voltage. The voltage is Vs, which is starting from 0 here, but the 0 of the current is starting at alpha by 2 after the voltage 0, and hence we say that the displacement factor here is cos alpha by 2. So, we can understand the displacement factor in this case is non-unity, it is cos of alpha by 2. So, the displacement factor is equal to cos of alpha by 2. So, in fact, if we make alpha higher and higher, this displacement factor will be lower and lower. It means the power factor of the current will gradually go down, and the converter will draw a lagging current from the supply, and this lagging current will create difficulty in power system. So, there is a solution to this. So, instead of using a single stage converter, we can go for a 2-stage converter. Now, before we do that, let us understand what is the plot between the reactive power requirement and the per unit voltage. So, we have this output voltage here, V naught is equal to V into root 2 by pi into 1 plus cos alpha, alpha is the triggering angle. So, what is VO maximum? Now, VO maximum is equal to V into root 2 by pi 1 plus 1, and that is alpha equal to 0. So, when alpha is equal to 0, the output is maximum. So, cos alpha is 1. So, that is VO maximum, and that is equal to 2 into root 2 V by pi. So, V is the RMS of the source voltage. V is the RMS of the source voltage, that is Vs. So, if we express this V naught once again in terms of V naught maximum, so we can say V naught is equal to V naught maximum by 2 into 1 plus cos alpha, or we can say 2 V naught by V naught maximum is equal to 1 plus cos alpha, and V naught by V naught maximum, this we can say this is equal to V naught per unit. So, we will rewrite this expression as 2 into V naught per unit, that is equal to 1 plus cos alpha, or 2 V naught per unit minus 1 is equal to cos alpha. So, we are trying to have a relationship between the per unit output voltage and the reactive power. Now, what is the reactive power here? The reactive power is Q, and Q is equal to voltage into current into sine of the angle between them. So, we can evaluate Q as follows. Q is equal to, what is the voltage here? V RMS is V. So, we have the V here into, what about the input current? We will go back and see the input current here. The input current is given by this expression, that is equal to 2 into root 2 IDC by pi, 2 into root 2 IDC by pi into cos alpha by 2. So, if we take this IS1, that is the RMS component, and then we have displacement factor is alpha by 2. So, it is 2 into root 2 IDC by pi into cos alpha by 2 is the RMS value of the input current, but then we are interested in the reactive power, and the reactive power is voltage into current into sine of the angle between them, and angle between V and I is alpha by 2 here, because we have a semi control converter and the current is lagging behind the voltage by alpha by 2. So, we will again multiply by alpha by 2, sine of alpha by 2. So, we have sine alpha by 2 here, and that is equal to root 2 V by pi into IDC into sine alpha, and that is equal to, we can say, Q maximum into sine alpha, because the reactive power here is maximum when alpha is pi by 2. When sine alpha is 1, it means alpha is pi by 2, we have the maximum reactive power. So, we can rewrite this in this following fashion: Q is equal to Q max sine alpha. And then what about our equation? We can write down this equation in the following fashion, or Q by Q maximum is equal to sine alpha, or we can say Q per unit is equal to sine alpha. So, we have equation 1 here, we can call this to be equation 1, let us say, and we have equation 2 here. So, equation 1 gives an expression in terms of the output voltage, and equation 2 has got expression for output, I mean the input reactive power. So, we can, from these two expressions, we can say from 1 and 2, we can say here 2 V naught per unit minus 1 whole square plus Q1 per unit square, that is equal to 1, and that we can say that is equation number 3. So, we know that sin square theta plus cos square theta is 1. So, we have from expression 1 or the equation 1 we have cos theta. So, 2 V naught pu minus 1 square plus q per unit square is equal to 1, and this equation 3 can be plotted. So, we can plot this equation 3 as follows. So, we can again rewrite this equation 3, 2 V naught per unit minus 1 whole square plus q per unit whole square, that is equal to 1. So, we can draw this graph. So, what we will do here, we will take V naught per unit in the x axis and q per unit in the y axis, and this graph we can plot. This will be something like this: the reactive power in the y axis and the output voltage in the x axis, and here we have 0.5 and here we have 1. So, we can see in this case that the reactive power is a function of the output voltage. It means when the output voltage requirement is very low, the reactive power requirement is also very low, and when we are gradually increasing the output voltage, the reactive power drawn is also increases. Let us say that here when the output voltage is low, it means it is close to 0, there is 0 reactive power, and this is because in this case alpha is in fact 0 here, we have 0 reactive power here, and then we reach half the voltage here, output voltage 0.5 per unit. So, in this case we have maximum possible reactive power, this is Q max, this is maximum, this is in fact 1 here, and then when we still increase this output voltage again at 1, this is corresponding to alpha equal to 0, and this is 0 output voltage, we have alpha is 180 here, alpha is 180 at 0 output voltage, and alpha is 0 at 1 per unit output voltage. So, when we increase this output voltage, the reactive power increases, reaches maximum for 0.5 per unit of output voltage, the reactive power is maximum, that is 1 per unit, and again when we increase this output voltage further, the reactive power decreases. This reactive power in fact is a big burden for the traction drive. When you have the traction drive, when the motors are being controlled, we have to vary the output voltage, and hence this reactive power requirement is also excessively high. So, in this lecture we have discussed about the locomotive, the drive rating, the various tractive efforts, and then we have seen how we can control the DC traction motor using tap changing transformer and also the semi controlled converter bench. In the next lecture we will see how we can have a two stage converter to minimize or to reduce this reactive power burden on the supply side. The source will have less reactive power when we, instead of a single stage converter, we go for a two stage converter. This will be discussing in the next lecture.